Welcome to our next lesson in chemistry. Today we are going to, in fact the next 2 weeks, our last 2 weeks of lessons, we are going to study more into nuclear chemistry and how that differs from the normal chemistry that we've been studying all year long. We're going to be in chapter 17, and we're going to be kind of starting to dive into a little bit of this uniquely different part of chemistry. So, in 1942, December 2nd of 1942, at the University of Chicago, a group of scientists got together at the stadium, and down underneath it they had a bunch of people that came, and there's a picture on the bottom of page 287 that's the first nuclear reactor there that's kind of showing this demonstration, an artistic impression of it. And there were stacks of carbon blocks and different kinds of blocks, and in there were some uranium blocks, and there were neutron counters, little type like Geiger counters that were around that were kind of clicking a little bit because there were things going on. And once they were ready to start, they pulled special rods out from between some of the uranium, and the amount of clicking just increased drastically from being just a little click, 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 click to being just really, really fast and sustained. And the head physicist monitored several of his little things and watched it for about almost a half an hour, about 28 minutes to half an hour. And then he ordered that these rods be pushed back in, and when they pushed the rods back in, it slowed back down and stopped. And he excitedly said that they had produced the first sustained nuclear reaction that was controlled, which was pretty exciting because that was the first reaction of this type. I don't know that it was very safe for those individuals who were there. We'll talk a little bit more about that as we go through, but it was a nuclear reaction that was taking place at an accelerated rate and controlled. Now that was in 1942. Uses for this nuclear type of chemistry range from things like the diagnosis and treatment of some types of cancers, some other types of diseases. In some cases it is used to treat food that goes on the shelves, and there's pros and cons to all these. I'm not telling you whether or not they're good or bad. There's a lot of people who feel like they're really damaging, but they use, a lot of times they'll radiate fruits and vegetables that are fresh so that they kills microbes that are on them so that they last longer on the shelf. There are certain types of medical supplies that have this type of radiation to make them last longer. Nuclear radiation is used to power most of the really large warships like aircraft carriers, submarines, things like that. A lot of spacecraft. In fact, even ones that are small spacecraft that are just unmanned, that are sent out into space, they have small little nuclear reactors so that they can have electricity being produced for potentially hundreds of years. And then lastly, it's used for generating power in a lot of places for the general power, electric power that comes to your homes. Now, we don't have any nuclear power generators like that are being used in Utah, but if you travel around the United States, you can see some. I've seen some in Washington State, up near Seattle and things like that. There's a picture on the front page of chapter 17, 287 at the top left, that shows a picture of a nuclear power plant. Those towers are just where the boiler is releasing steam. That's not releasing radiation. that's releasing steam as they cool and generate the steam that is then used to turn the big turbines that turn the electric power plants. And what the nuclear power is doing is it is heating materials that then are transferred through a staged process to where it heats the clean liquids that then are used to generate steam to create the electric power. This is a very important field of science currently. It's used in the generation of power and things like that. It's also used in the situation of weapons, which the first time in the history of the world where they were used was as a weapon was during World War II, when the United States dropped 2 bombs on Japan, on Hiroshima and Nagasaki, and which helped to convince the Japanese government that it was worth giving up and ending the war. There's a lot of people who say that was really a bad thing. Others say that it saved probably about 1 million US soldiers, because Japan would have been harder to have conquered than some of the islands where we had lost tens of thousands of soldiers in conquering some of these islands, and that Japan would have been that many by 100-fold or more. So some estimates say that there would have been close to 1 million US soldiers that would have died. Not to mention, probably many times more Japanese would have died actually than those that died in the cities. Now, let's talk a little bit about the differences. So all through chemistry, what we've been studying, we've been talking about the bonds between one atom and another atom, like water. So with water, we have oxygen, which is a smaller sized atom, but much larger than hydrogen. And then we have 2 hydrogens that are bonded through an actual molecular bond to these others, and they create a completely different characteristic. Water is not at all like oxygen, and it's not at all like hydrogen. When you put 2 hydrogen and oxygen together, you get water. And many, many compounds that are created like this have no similarities whatsoever to what made them. Last week we talked about hydrocarbons. You have carbon, and then you put hydrogen to it, and you get things such as natural gas, or things like gasoline, paraffin wax, diesel, plastics. I mean, depending on the combinations, but most of those have absolutely no characteristic look like a hydrogen atom or a carbon atom. Now, when we're talking about nuclear chemistry, we're not talking about that kind of bonds, because those kinds of bonds, the bonding itself has everything to do with the outer electron shell and has nothing to do with the inner, or very little, if any, to do with the inner nucleus of the atom. So we've talked about the outer shell, that most atoms want to have 8 electrons on their outer shell, and so depending on how close they are to 8, they either give up some or share some or take from another one, depending on how many they have, and we've gone a lot over the year over that, to try to get that balanced, full electron shell. And that's what causes that bonding. Well, nuclear chemistry is a completely different thing. So when nuclear chemistry happens, we do something, or something naturally happens to the central nucleus. So if this is the nucleus, and we've got all these electrons going around that have a lot of space. I mean, there's a lot of space between the nucleus and the electrons per their size. Like if this was the nucleus, the nearest electron would probably be way down by Mona Reservoir or something like that. I mean, there's so much space, just like there is in the universe of space between stars. Same thing with atoms and things like that. But if this is our nucleus, and it's something like helium, then there's 2 protons and 2 neutrons on the standard helium. And they're happy, they clump together perfectly, everything's all happy with them. Now, in the past we talked a little bit about carbon-12, which when you look at the periodic table, you can see that it has 6 protons, but carbon-12 means that it has the standard average carbon has 6 neutrons, so there's 6 protons and 6 neutrons. Now, there's a type of carbon that is generated in the up in the ionosphere, up in the high atmosphere. When solar radiation hits it, some of it is bounced around and creates what's called carbon-14. What happens is it's still carbon because the atom is defined, what atom it is defined by the number of protons, not necessarily by how many neutrons it has. And so carbon has 6 protons, and carbon-14 just added 2 more neutrons to it to make it be carbon-14. Now, when that happens, it's not super stable. And because it's not super stable, there's an extra neutron that's kind of wobbling around on it, and it doesn't really want to stay there, and eventually it flies off. And that causes carbon-14 radiation. Now, I've talked to you about this quite a bit in our class about how that happens at a very predictable rate, how often that happens, and there's a pretty predictable amount of carbon-14 that's averaged out. I have carbon-14 in my body, you have some in yours, the food that you eat has carbon-14 in it, because a certain percentage of all carbon on the earth is carbon-14. And at any given time, it's fairly consistent. Now, there can be things that can raise the amount of carbon-14 in the air and lessen it, and those kinds of things can affect the percentages at a given time, and that's one of the reasons why carbon-14 is somewhat of a guess as to how old something is because when something dies, it doesn't take on any more carbon-14, and slowly but surely that carbon-14 changes, and if they know how much there is, they know how fast it changes, and they can kind of predict how old something is. The difficulty is knowing exactly how much carbon-14 there was, say, 10,000 years ago or 6,000 years ago, because if there's a different amount, that could drastically change the years that they calculate. And so there's some questions as to how accurate that is, but that's the carbon-14 is a radioactive chemical. It gives off some form of radiation. Now, here again, it's not a major dangerous form. Everybody has a certain percentage of that. Every living thing on Earth has the exact same average amount of carbon-14 in them. Now, back to the regular nuclear stuff. So, in the early 20th century, chemists started to discover that some isotopes, which the carbon-14 is one isotope and carbon-12 is a different isotope of the same element, but they started to discover that certain isotopes had this characteristic of giving off invisible rays. Some kind of radiation, they didn't really call it radiation so much at the time, but they would give off these invisible rays, and there were a lot of interesting things that were found with that. If you flip over the page to 288, where we talk about the discovery of radioactivity in that, they found that some of these rays would penetrate things, like some would go through a brick wall and some would actually be stopped by something as thin as a piece of paper. But they started to notice these things, and one individual in the early 19th century, or the late 19th century, early 20th century, was messing around with some uranium, and he wanted to see if he could do something to the uranium and cause it to affect a photoplate. So a photographic plate is something that when you take it and expose it to the sun, it changes the chemicals on it, and if you do it right, then you can get a photograph from it. And that's how, up until the new digital age, how almost all of photographs were done for the last 100, 200 years, 150 years, was with these photographic plates. And so what he wanted to do is he wrapped this photographic plates or photographic film in a material that would not allow any light into it. And then he took a piece of uranium and set it next to it and then exposed the uranium to sunlight, because he said he felt that that would cause it to fluoresce and give off energy. And when he did that and then took the plates and tested them, sure enough, they were exposed. And he thought, wow, sunlight causes uranium to give off this energy. Now, he wanted to do another experiment, and when he was to test a few more things, and it was cloudy outside. So he took the uranium and the photographic materials that were protected and just put them in a drawer and left them there for a few days. And when he went back, he just decided, well, I'm just going to test these plates as they currently sit. And he found out that they had very heavily been exposed. So the uranium was actually sending and causing the photographic plates to be exposed even when they didn't have sunlight directed on them. So that was one of the experiments that proved that something was going on, and that there were some kinds of rays or some kind of energy that was being released. Now, in the late 1800s and the early 1900s again, there was a husband and wife, Pierre and Marie Curie, and they were messing around with a different type, a couple of different atoms than uranium. One of them was thorium. Now thorium is, if I can find it here, and radium. So this is radium right here, and for some reason my mind is not finding the thorium. Yeah. So they were messing with thorium and radium. See if I can find that thorium for you. I should have looked that up. Sorry about that, I'm not finding the thorium. Which number is it?
90.
90?
TH.
Okay, yeah. So it's down here, radium and thorium. Sorry, should have known the thorium was down there, because if I had thought about some of the reactions we'll talk a bit later, I would have known that's where it was. Okay, so thorium and radium, they were messing around with those. And in the process of doing it, they started to find out that they gave off invisible rays, just like uranium did. And they were the ones that gave it the name radioactivity. And so they called it radioactivity because it was giving off some kind of invisible rays, in some ways very similar to the electromagnetic rays that are given off by a radio and things like that. So they called it radioactivity. Now, they also discovered a brand new element that had never been found before, or known of before, and they called that polonium. And polonium is this one right here. So, element 84. And they called that polonium after naming it after Poland, which is where Marie Curie came from. And they called radium, they also gave radium its name because of the radioactivity. Now, they were some of the first ones to really start to learn some of these things, and there were some scary situations that would happen with some of their studying. If I'm not mistaken, both Pierre and Marie Curie both died of cancers and things like that because they didn't understand how dangerous these radioactivity things could be to their bodies. Like I mentioned in the earlier electropop, when they first did the first sustained thing, I don't know how much damage was done to a lot of those scientists who were studying at that time because they didn't understand a lot of what they were dealing with. It was a few years later when they did that, but they might have understood enough to keep them somewhat safe. Now, so we call this activity that takes place inside the nucleus, not the electrons, inside the nucleus, where it's unstable and it doesn't want to just sit there and be happy. It's moving around and shifting, and sometimes it'll send off electromagnetic radiation in a waveforms that come out. It actually even can send particles out. We'll talk a little bit about what those particles are and how those look in a bit later. But so one of the first things that they found was X-rays. Now, these X-rays that were the same things that were causing that film to be exposed earlier and things like that, they found these X-rays, and X-rays are high energy, very small electromagnetic waves. And if you've ever been to the dentist or you've had a broken bone, they use X-rays to be able to shine right through your body. And when they hit something really dense, such as a tooth or a bone, then it doesn't penetrate as well, and that's why when they put the plate behind it and that stuff shines through, everywhere it shines through without hitting anything, it exposes it a whole bunch, and that causes it to be black. And when it hits something that's more dense, less gets through, and that's where it gets the lighter parts. That's how you see the whiter bones or the white teeth, because it's blocking that radiation. Now, so we've talked about the fact that they're stable and unstable. Carbon-12, very stable, it doesn't ever change. Carbon-14, unstable, and it eventually releases and breaks apart a little bit, and as it gives off and becomes something other than carbon when it does that. Now, so no matter how hot you get an atom, you put it under a flame, it burns, we have these chemical reactions that happen. The atoms are still atoms. You may break them apart. Like if we break water apart, it's still oxygen and hydrogen. You didn't affect the atoms, all you did was change the molecule. That's molecular chemistry. When this radiation type stuff starts to happen and these atoms start to break apart, they actually become a completely different atom when they're done. So carbon-14, when it breaks apart, doesn't stay as carbon. It doesn't just give off a couple of neutrons. I believe it actually gives off what's known as an alpha particle, and so it would become a completely different atom when that happens, and we'll go into that just a little bit more in a minute. So when these things are ejected from the nucleus. It can be the electromagnetic radiation, which is like radio waves of different energy levels, or it can actually be particles. And these subatomic particles are called subatomic because they're parts of or smaller than the other parts. These subatomic particles can be ejected sometimes at pretty high speeds and sometimes at slower speeds. Obviously, if something has more mass when it's ejected, like an alpha particle, it's going to be moving slower. And that would be something that would probably be stopped by just a thin piece of paper. It would stop an alpha particle. But it doesn't matter whether it's particles or the electromagnetic radiation, it is still called radiation, nuclear radiation, because it's stuff that's coming out, and that's nuclear radiation. It's coming from the nucleus. And any atom that has this nuclear action that's taking place in the nucleus is called radioactive. It's giving off some form of radiation, be it particles or electromagnetic. It's going to be called radioactive. Now, there are many small little parts that are called nuclides, which are just small particles, and they are always discerned and talked about by their atomic mass, by their mass and their atomic number, both. That's why it's carbon 14. We're talking about the difference, so you need to know both. If you're talking about uranium, there's several different uraniums. Uranium, if you look right here, 92, and its mass is 238. 238 is the most common uranium that you're going to mine. 90% of it's going to be that, but there are some that have a few less particles, but those few less neutrons. It's uranium-235, which is much more radioactive and has a lot more explosive ability. And so a nuclear weapon that was using uranium would want uranium-235, not 238, because 238 is just a little bit stabler. Because it's not just about how big it is, but it's how they intermesh with each other and how they make their connections. And uranium is big enough that it's kind of flopping around always, and 238 is still radioactive, just not as much. Now we're going to talk about the actual rays that come off. There's called an alpha ray, which is an alpha particle, and it's made up of 2 neutrons and 2 protons. So it's the exact same thing as the nucleus, the full nucleus of a helium atom. Because a helium atom has 2 protons and 2 neutrons. The alpha particle is that. So if an alpha particle comes off of carbon 14, that means it has 6 protons, but as it releases 2 of those, it's going to drop 4, and it's going to become beryllium. It'll actually release 2 of them, and take 2 of the neutrons with it, and it will become beryllium now, which would be a completely different atom once it breaks apart. When something like uranium breaks apart, it breaks into two different particles, and it becomes a lot smaller. Here again, we're going to go more into that as we get down, but that's the alpha particle, and it's actual particles. The next particle that sometimes is emitted is a beta particle, which is an electron that gets thrown out, but it comes out of the nucleus as opposed to an electron just floating around, and it's where you end up breaking parts out of the neutrons or whatever broken up, and they eject an electron. And then lastly, you get electromagnetic radiation that comes out, like radio waves, but the ones that usually come out of these elements are extremely high frequency with a lot of energy, and they're things like X-rays, and there's even some that are more dangerous than X-rays because they're even smaller than X-rays are. and have even more energy than X-rays, and those are called gamma rays. And those are the ones that are super dangerous instantly. I mean, not that X-rays can't be dangerous in high doses either, but gamma rays go through and they actually hit atoms inside your body with enough energy that they can kind of break them apart, and it can change the chemical composition of something. If it was to hit one of the hydrocarbons and break the carbon so that it wasn't quite what it was supposed to be, then all of a sudden it's a different molecule altogether. So you can see that it could be quite damaging. And that will finish today's lesson. Tomorrow we will, on our next lesson, we will continue the study of nuclear chemistry.